This week in class we talked about rational and irrational numbers. And this really should just be a review for you because in 8th grade you should have done some rational and irrational numbers. In fact, in 8th grade you had to rank them, you had to say which one was larger, we saw them in Pythagorean theorem. So you really should remember rational and irrational. Just in case you don't, I have some vocabulary words though, okay? And these are our two main ones. And it is radical and radicand, which this is one of my favorite words because it's so fun to say. I mean, I think so anyway. But the radical is actually the square root symbol. That's what most of us call it. But guess what, guys? This actually is not just a square root symbol. I can put any number in here, and that's called the index, but you don't have to know that. And it would would no longer be the square root symbol. It could be the cubed root symbol, the fourth root symbol. So we really want to get out or get away from calling this the square root symbol, and we want to just start saying, hey, that's a radical. All right, the radicand is actually the number that's inside of our radical. So it's this guy right here. And I just like to refer to him as the radicand because it's a fun word and it makes you sound smart when you say it, especially in college. Professors love that. All right, for this one right here, I do have a definition of irrational numbers. Now remember, this is Ms. Fruget's definition. You're probably not going to find this even on Wikipedia, you probably wouldn't find this. And you're probably not going to find it on the internet either. But my definition, which we talked about last year as well, was an irrational number is any number that when written in decimal form goes on forever without a pattern. Or you could consider it to be a number that can be rewritten as a fraction. And basically the reason why we can say a number that can be written in fraction form is because the only numbers that you can write in fraction form, they're not going to go on forever without a pattern in decimal form. So that's why these two definitions are related to one another. Now that's the fancy way of saying it. But let me show you some examples of irrational numbers. And most of the students this week, when I said, give me an example of your number, they said, Ms. Fruget, pi. And you know what? They're correct. That is an irrational number because it goes on forever without a pattern. All right. Some other irrational numbers that especially the students tended to forget was if I had the square root of, let's say, 5. The square root of 5 would be irrational because there's no answer for the square root of 5. Can you think of one? You probably can't because there's not one, friends. It would be a decimal that would go on forever without a pattern as well. So since we can't just round it, we're just going to say it's always the square root of 5. Just like pi. They say pi is 3.14. Yes and no, because the rounded version of pi is 3.14. But pi itself is not 3.14. It continues to go on forever without a pattern, just like the square root of 5. So some other examples of irrational numbers would be like square root of 7, square root of 24. All of these don't have perfect answers. So here's Ms. Fruget's simple definition that you will definitely not find anywhere in a math book. But my simple definition just says that an irrational number is any radical that does not have a perfect answer. And by that I mean, I don't know what the square root of 24 is. I don't know what the square root of 7 is. So they're irrational. Now if I did give you, let's say, the square root of 100. What's the square root of 100? 10. Since it does have a perfect answer, then this number is not irrational. It's actually called rational. All right, and that's just a recap just to help us remember. Now the standard, if you recall from the first slide, it's not in 9th grade. They don't want you to be able to say, what's a rational number, what's an irrational number. They want you to be able to look at sums and products and to determine would that sum or would that product be rational or irrational. So let's go ahead and look at some rules for that. Once again, this is Ms. Fruget's rules. You're not going to find this in a book anywhere, maybe not even online. But this would say shortcut if this icon wasn't in the way. However, for adding and subtracting, this is what you do. If just one of your radicands is irrational, then the entire sum or difference will be irrational, which basically means if just one of my radical numbers is irrational, then my final answer is going to be irrational in the end. All right? Multiplying, in order to figure out if your product would be rational or irrational, you're going to have to multiply the radicands together And then you can determine if the product would be rational or irrational. So let's go ahead and look at some examples. Have it on this screen. And this is multiplying. All right, so when we're multiplying, we do not look at each individual radicand. What we do is we multiply the two together. So what is the square root of 5 times the square root of 6? Square root of 30. Does the square root of 30 have a perfect answer? No. So that means this is irrational. And because I'm going to be lazy, I'm just going to write an I instead. Okay, the square root of 5 times the square root of 5 is the square root of what? 25. And is there a square root of 25? Yes, because that is 5. So guess what, guys? That means that this is rational. So that just means your final answer would be rational in the end. Your product would be rational. Okay, let's look at this problem down here. 50 times 2 would give me the square root of 100. Is there a perfect answer? Yes, and it is 10. So that means that our final answer would be rational. And then if we come down here again, have the square root of 8 times the square root of 2, which is the square root of 16. That does have a perfect answer, which is 4, so that means my answer is rational. Let me go ahead and give you a freebie problem. Freebie meaning that I'm creating it up right now. It wasn't really in the lesson. But if I had the square root of 5 times the square root of, I don't know, 8. All right? What's the square root of 5 times the square root of 8? Square root of 40. And would that be rational or irrational? Irrational. So that means the product is irrational. Okay? We're going to move on to adding and subtracting. And here I'm just going to call this the sums because for most of these problems we're at least adding some. But note, please take a note that saying the sum or the difference would be the same thing. Alright, now this is a little bit different than multiplying the numbers together because what we want to do with these radicals is we want to look at each individual number. You cannot combine them. So the square root of 7, is that rational or irrational? Irrational. Square root of 2 is also irrational. Square root of 4 is rational. If only one of these numbers is irrational, guess what, guys? That means your whole sum is irrational. All right? Let's go ahead and look at this example. What about the square root of 12? Irrational. Square root of 6 is also irrational. Pi is also irrational. Every single one of these is irrational, but remember, all we need is just one number to be irrational, which just means if one of them is irrational, then the whole thing is. But if they're all irrational, they're still all irrational. All right? Square root of 4. Well, that answer is 2, so that must mean that this is rational. The square root of 1 is 1, so that means this is rational. The square root of 9 is 3, so that means this is rational. And if I look, I have all rational radicals, which means that my final answer will be a rational number. Now, in Algebra 1, we're not learning what is this final answer. All we're learning is to be able to predict, is it going to be a rational answer or an irrational answer in the end? Okay, looking at this problem right here, just still you can look basically at the radicals, okay? You don't have to worry about this number unless it was pi. If this number was pi, if pi shows up at all in your problem, it would be irrational. But since it's just 2, we're okay. We just stare, or not stare, we just look at what's inside our radicals, okay? Our radicands. So that means this would be rational, but this is irrational because there's no such thing as a square root of 7. Well, there is a such thing, but it's not a perfect answer. And whenever we look at those two, we see that at least one irrational shows up, so that means that our whole problem is irrational, okay? And then the last example, remember, we're not really going to look at the coefficients. I'm just going to go ahead and do this. The square root of 25, well, that's rational. Square root of 100 is also rational. The square root of 64 is also rational. So as long as no number is irrational, then your whole answer will be rational. Once again, we're not predicting, well, we are predicting what the answer will be. We're not trying to solve what is the actual answer. Okay, on the next slide, I just wanted to give you some extra practice. And if you want, let me go ahead and actually draw my time symbols because I did not do that before, sorry. If you want, you can pause the video and you can try these. So if you just want to look at them, go ahead and pause the video right now. And that way you can take some time just to work these by yourselves and just determine would it be rational or irrational. All right, so I'm going to give you a second. Go ahead and pause. And then press play whenever you're ready to check your answers. Okay, guys, I'm assuming that you press pause and now you're pressing play because you want to check your answers. And let's go ahead and go over what you determine. Well, whenever we're multiplying radicals, that means that we need to go ahead and multiply them. So 4 times 3 is 12. That is an irrational number. Okay? Square root of 9 times square root of 4 would be square root of 36, but there is a perfect answer, so that means it is rational. The square root of 20 times the square root of 5 would give me the square root of 100. Does have a perfect answer, so it's rational. The square root of 8 times the square root of 3 is the square root of 24. Does not have a perfect answer, so it is irrational. All right, looking at our bottom ones, I'm going to change colors real quick. The square root of 5 is irrational. 19 is irrational. 25 is rational. As long as one of these is I, or at least one of these is I, then the whole thing is irrational. So my answer is irrational. This is rational. This is rational. And this is rational. So that means that your whole answer that we're predicting would be rational in the end. Okay, last one on here. 12 would be irrational. 100 is rational. But if at least one of them is irrational, then the entire the answer would be irrational in the end. Okay? Let me go ahead and just show you one more type of problem, and I'm going to just a freebie problem again. If I had pi times the square root of 4 minus 3 square roots of 9, would this be rational or irrational? I'd kind of mentioned this a little bit earlier, but I want you to notice that even though this is rational and this is rational, your final answer would not be rational in the end because you have pi right here. Anytime pi shows up in the problem, it's going to be irrational. The only time it goes back to being rational would be if the pi's canceled out, which more than likely in Algebra 1 is not going to happen. However, if you're in college and you're doing pre-calculus or calculus or trigonometry, sometimes that pi will cancel out. So you just have to watch and look, but for Algebra 1, typically it won't. All right, and that covers it for this week's lesson on rational and irrational numbers. Thanks for watching.